Welcome back. Okay, last couple of classes we discussed about scalar couplings and gave a lot of information about how to arrive at the information, how to get the information about scalar coupling in a different multiplicity examples I gave. For example, when do you call a spin system as doublet of triplet, triplet of quartets, quarters of triplet, triplets of quartets, various examples we took. And at the end of the last class, I also introduced what is called Popel nomenclature. It is the nomenclature used to describe the spin systems to enable analysis of the NMR spectrum. In that, I briefed you about what is strongly coupled spins and what are weakly coupled spins. I distinguish between strongly coupled and weakly coupled spin system. Of course, in the weakly coupled spin system, I discussed and I said when the chemical sheet separation between two coupled spins is sufficiently large, then large compared to coupling constant. Let us say the ratio of chemical sheet separation to that of the J coupling, when delta delta over J between two coupled spins is sufficiently large of the order of more than 50, then I told you such systems can be treated as weakly coupled spin systems. And such weakly coupled spin systems, the spectra are easy to analyze. Their straightforward analysis is possible. Also we call them as first order analysis of the spectrum. Whereas if you go to the strongly coupled spin system, the condition for which is the chemical shift separation between two coupled spins is comparable to that of the coupling constant. In other words, if I take the ratio of delta delta, that is the chemical shift separation to that of the J coupling, that is delta delta over J, if you take, then I also said it so happens then the spin system are strongly coupled and the spectra are not amenable to first order analysis. In this sense, you need to adapt different method to analyze such spectra. And the intensities are very well described in the weakly coupled spin systems. For example, if I take two spins which are weakly coupled, A and X, we can calculate intensities and show that all of them have equal intensity. But it is not the case with strongly coupled spin system. And I also introduced the notation of Popel for the spin system when they are chemically equivalent. What happens? How do you define Popel notation for a chemically equivalent spins? One thing. And I also describe the notation for the groups of chemically equivalent spins present in the molecule. For example, if you have a CH2 group, if you have a CH3 group coupled to some other proton, how do you define the spin nomenclature? So all such examples we discussed. And now we go ahead in analyzing some of the spectrum. For example, we start with today single spin systems which gives multiple peaks. I gave the example of different spin system. It can be one spin system, or two coupled spin system, three coupled spin systems, and I said what are the possible spin systems we can think of. In a single spin, of course, no question of any discussion. It has got only one spin and only two energy states, alpha and beta. Spins undergo transition between these two, and then we are going to observe a single peak. And I gave several examples for that molecule like CHCl3, CFCl3, etc. And for two coupled spin systems, I told you there are three possibilities we can think of. Weakly coupled A and X, two spins are weakly coupled. Strongly coupled A, two spins which is AB, and even more strongly coupled in the sense chemical shifts between two spins are exactly same. That is, chemical shift between of A and X overlap, and the coupling between them is not seen in the spectrum. That we can call as A2 spin system. So there are three such things possible. When I go to three coupled spin systems, I said there are 10 such spin systems we can think of, and all of them can be analyzed very easily in a different way. So there are ways of analyzing this. Today, let us start with analysis of a single spin case first, which gives multiple peaks. Right? It's something difficult to imagine also. How, for example, a single spin in a molecule can give multiple peaks. Last week I was telling you about this. Look at this. This is a simple molecule, CFCl3. Now I am looking at the fluorine 19 NMR spectrum. When I'm looking at the fluorine 19 NMR spectrum, interestingly, we got 4 peaks. Mind you, I wanted to tell you carbon 13 is in its natural abundance in this molecule. So coupling is only 1% of the carbon. Let us say there are 2 types of isomers. Carbon 12 isotopomer, which is 99% abundant. Carbon 13 isotopomer is only 1% of abundance. So carbon 13 isotopomer we are not considering. We will consider only carbon 12 isotopomer of this molecule. And I also said last time, and again repeating, chlorine is a quadrupolar spin, which in this case I tell you is not coupled to fluorine at all. It doesn't couple. It may facilitate relaxation, that we will worry later. But now present this molecule, I am telling you, I am considering carbon 12 isotopomer and chlorine is not coupled to fluorine. Then how many peaks I must expect? Logically, if you look at this molecule, there is only one isolated fluorine which is not coupled to anything. That means I must get only single peak for this fluorine spectrum of this molecule. Interestingly, we are seeing 4 peaks. This is with 100% abundance. This is 100% intensity. This is 95% intensity. This is 30% intensity. There is another small peak here. If I enlarge the intensity scale, you will see it is 3% intensity. And I want to repeat, this is a real spectrum. Don't get confused, it's not impurity or anything. It's a real spectrum. Now the question is, how, when we are looking at a single fluorine which is present here, can give rise to 4 such peaks? And now the question is, we have to understand this. So what I am going to do is, this is called isotope shift in NMR spectrum. We will take an example of this molecule and interpret the spectrum. We will go ahead further in the next 1 or 2 classes and the subsequent classes. I will discuss more about the chemical sheets. I'll come to that point later. Okay, but for this example, we will analyze the CFCl3 spectrum and find out why we are seeing 4 peaks. Now the thing is, first before interpretation, we should understand isotopes of chlorine. Chlorine has 2 isotopes. One is chlorine 35, which is 76% abundant. Other is chlorine 37, which is 24% abundant. Understand the thing what I am telling? Now we have to discuss about isotope shifts. As a consequence, we have to find out the number of isotopes of chlorine. I said there are 2 types of chlorine isotopomers. One is 35 and other is 37. One has 76% abundance, other has 24% abundance. Now let us consider the possibilities of isotopomers present in this molecule. This is my CFCl3 molecule. This is fluorine. There are 3 chlorines present here. Let us consider the situation. What is the possibility of population of an isotopomer where chlorine 35 is present in all the chlorines? If all chlorines are isotopomers of chlorine 35. I understand things very clearly, I am telling you. Let us say all these chlorine 35 are isotopomers of, all these chlorines are isotopomers of chlorine 35. Then what is the percentage of population, probability of population you can expect? Now in this case, in all are 35, let us understand it is 76% abundant. 76% of it, I took 0.76 for this chlorine, 0.76 for this chlorine, and 0.76 for this chlorine. multiply all the three, I get 0.438. This is the population when all the chlorines are in 35 isotopomers in this molecule. So if I say I have only one molecule of CFCl3, one type of molecule isotopomer, where all the chlorines are in 35 isotopomer position, in which case I'll get 0.438. I'll normalize this to the intensity 100%. Understand? If only all chlorines are 35 isotopomers in this molecule, we have an isotopomer of CFCl3 with all the chlorines in 35, we must get only one peak. I normalize this for the intensity of 100%. Now what is a possibility 2? There is other possibility we can think of. When two chlorines are 35 and one chlorine is 37 isotopomer, it is possible, right? Look at this one. Now this chlorine can be 37, chlorine 37. This can be 35, this can be 35. But remember, there are three such possibilities. Now I said this was 37. Now this can also be 37, and this can also be 37, and I'm sorry, there is okay, it's fine. And this is 37, this can be 35, and this can be 35. Fine. Another possibility is this is 37 and these two are 35. There are three possibilities I can think of. Think of a possibility when two chlorines are 35 and only one chlorine is 37. There are three such possibilities. Any one of them can be 37, other two can be 35. So three such possibilities. Now consider the population in such a case. When one chlorine is 37, you can find out what are the possibilities. When okay, what is the percentage of abundance I found out? I said chlorine 35 is 76, 37 is 24. Okay. Now in this case 35 is 76% abundant. We'll put 0.76, 0.76 for two chlorines which are 35 and 0.24, 24% abundance for chlorine which is 37. So this is the population for any one of these isotopes. Multiply all these things, I think it is 0.138. I simple plug in this number into calculator and you will get it as 0.138. But this is for one of the isotopomers. But we have three such possibilities. So multiply this by 3, the intensity turns out to be 0.415. Now compare this intensity with the original first possibility where all were 35. Now normalize this other one, it is 100 by 0.438 into 0.415. This turns out to be close to 95%. It's simple arithmetic. You don't have to do anything. Okay. Now for all the three possibilities of the isotopomers where two chlorines are in 35 and one chlorine is 37, the population if you calculate, it turns out to be 95% population possibility of that. Is there any other possibility we can think of for isotopomers? Yes. Now two chlorines could be 37 and one chlorine is 35. That's possible. So this is 37, this is 37, this is 35. True. These two are 37, this is 35. These two are 37, these two, and this is 35. So now calculate the population for this. Now one is chlorine 35 is 76%, put 0.76. Chlorine 37 is 24% abundant. There are two such chlorines, 0.24 into 0.24. You multiply. What did you get? 0.044. It is a simple arithmetic. This is for one type of isotopomer, one isotopomer here. One possible. Now there are three such possibilities. Multiply by 3. You get it 0.132. Now normalize the intensity of this with respect to the first one where all chlorines were 35 I took that as a standard for 100%, right? Population where the intensity is 100%. Now normalize this with this 100 divided by 0.132 into this first normalized one it turns out to be 30%. Very interesting. Now, what is the last possibility we can think of? When all the chlorines are 37, how many possibilities are there? Only one type of isotope is possible in that. Okay, all the chlorines are 35, all are same, and actually there is no need to consider this, and this. Now, when all the chlorines are 37, there is only one possibility, and you calculate the population of all of them, 0.24 into 0.24 into 0.24, it turns out to be 0.0134. Normalize this with the situation 1 where all the chlorines were 35. Now, what is the percentage you are going to get? 3%. Now, we understood everything. There are 4 different types of isotopes are possible here. When only one possibility where all the chlorines are 35, which I took as a standard 100% intensity. Second, when one chlorine is 35, I'm sorry, 2 chlorines are 35, one is 37. We got 95% intensity. Population now is 95%. When one chlorine is 35, 2 are 37, there are again 3 such possibilities. When we normalize and the intensity we obtain, it is 30%. The last possibility we can think of, all the chlorines are 37. Only one such possibility. When we normalize the intensity with the first one, it turns out to be 3%. So the intensity ratios of peaks in the 19 spectrum are 100, 95, 30, and 3. So you understand now, this is 100, 95, 30, and 3 arising due to statistical distribution of isotopes. Generally, isotopic shifts are expressed in parts per billion. You understood the now we will go back to the original spectrum which I showed you. This is the CFCl3 spectrum, and we worked out the intensity. This is 100%, and this has to be the peak coming when all the chlorines are 35. Only one possibility. This comes because when two chlorines are 35 and one chlorine is 37, there are 3 such possibilities. The intensity, when we calculated, it turns out to be 95% population. The population for this one is isotope is 1, where one chlorine is 35, 2 chlorines are 37, and 3 such possibilities. And when we calculated the populations and the intensity here turns out to be 30. Now, this is the last possibility where all the chlorines are 37, only one such possibility, we got 3% intensity. Very beautifully we can understand the spectrum. Remember, it is a single spin system can give multiple peaks. This you don't get confused. The interpretation is because it is due to isotopic effect. And you find out the difference between these two. What is the difference? There is only one, all the 3 are 35 here. Only one is 37, and isotopic substitution effect on the chemical shift, take out the difference, it is very small. And take the difference between this and this and this and this. You can find out what is the chemical shift effect of different isotopes on the chemical shift, how much it has shifted due to isotopic substitution. And this is due to isotopic effect. Okay, very clear now. Now, if you calculate this, I can tell you one interesting things are happening. The heavy isotope always shift the fluorine signal to the high field. Heavy isotope generally shift the peak to the high field. So now you take the difference in the chemical shift between this and this, it has shifted by 6.412 ppb. I took this as a reference, CFCl3, and if you take this one, this is plus 6.412. When I take the other possibility, it has moved this side, it is minus 6.4, I approximated 6.4. And to take this one, because now there are all the 3 are chlorine 37, it has shifted by 12.78 ppb. See what it generally, this is the peak which we always use as a reference in fluorine. That's why we took this as 0, where chlorine 35 is 2 and only 1, chlorine 37 isotope. With respect to this, how much peak has shifted, we can calculate. And shifting the positions of the peaks because of the isotopic substitution is always expressed in parts per billion. Okay, so we can start worrying or discussing all these things later, and the isotopic shifts are discussed. I'll come to this more detail later. But at the moment, I just wanted to tell you, sometimes when you look for a single spin system where only one proton or one fluorine is there, or you expect only one peak. Sometimes it so happens you may get 3 to 4 peaks. I wanted to bring to your attention, don't get confused. It is not because of any other reason, it's only because of isotopic effects. Now consider next possibility of spin systems when two nuclear spins are coupled. What are the possibilities? First, we'll consider AX spin systems. That is, A is here, X is the far off in the alphabet, That means when it is far away, it is a weakly coupled spin system. This is A and this is X. And the coupling between them is JAX. The spin coupling between A and X is JAX. Now, what are the two possible spin states for this? Remember, when we worked out the allowed transition, possible transitions in two weakly coupled spin system, we also worked out what is the magnetic quantum number for each of the spin state we took, and then each possible orientation of each spin, and then for each energy state we worked out the total magnetic quantum number for the state where two spins are in alpha state, it is +1, it is alpha beta, it is 0, beta alpha, it is 0 because minus half and plus half, and for a beta energy state it is -1. Remember, I don't have to go into the details, I discussed this earlier. There are only 4 energy states for this, corresponding to 4 different possible orientations of this nuclear spins. And both the spin states are in alpha, it is +1. When this is alpha, this is beta, it is plus half and minus half. The total magnetic quantum number of that energy state is 0. In this situation, my beta alpha also is 0. And the last possibility is beta both are down, it is -1. And now I'll put one important condition for this. Not a condition, it is true, it can happen. For a weakly coupled spin case, delta A is not equal to delta X. It should be true because the chemicals should have to be far away separated. That's so A and X chemical shifts are not equal. Secondly, delta of AX, chemical shift difference between A and X, has to be sufficiently large. Remember, one of the conditions for a weakly coupled spin system, this delta by J has to be greater than 50. That's what I said, at least of that order. That is one condition. Secondly, JAX is non-zero. If JAX is 0, it will become a different type of spin system. I'll tell you that later. And this AX can be both homonuclear spins and heteronuclear spins. Two spins could be homonuclear, or two spins can be heteronuclear. So in this case, in the AX, we also discussed earlier, when two spins are coupled, weakly coupled, well dispersed doublets will be there. One doublet for A, one doublet for X. Very easily you will see 2 peaks for each of them. And of equal intensity. Remember, there is no intensity anomaly here. All of them of equal intensity. We put it as a ratio 1:1:1:1. Okay, there are 2 weakly coupled spins will give rise to 4 peaks of equal intensity. And you do one thing, analysis will become very easy. There are 2 peaks here and 2 peaks here. Center of this doublet gives you chemical sheet of one of them. Center of this doublet gives you chemical sheet of other one. And the separation between these doublets will give you J coupling. So very easily, this is called first order analysis. If you can analyze the spectrum, simply without going into much mathematics or computation, It's a first order analysis where you can directly extract the chemical shifts and coupling information. Now, of course, how it comes, I already explained to you. I don't have to go to this in detail. And alpha, alpha, and beta, beta states are unpaired spins get destabilized, and actually, in that case, they have more energy. In the other case, when alpha, beta, beta, alpha states, they are paired spins, and it will be more stable. Okay. As a consequence, I said the energy level get destabilized, and we could arrive at the possible transitions. So now we can easily work out also. This remember alpha alpha and beta beta states destabilize, the energy levels will shift up by J by 4. Alpha beta and beta alpha states are destabilized and the energy is decreased by J by 4. So all four possible transitions we understood. We worked out last time, remember, but I did not give you the frequencies and other, what are the possible, how do you get frequencies from these things. I only show you four possible transitions where we identified 2 for A and 2 for X. Now I am going little bit more in this. I'll give you more example, more information, and the energy eigenvalues. These are called these are all the eigenstates. As if you find out, and the eigenvalues of these things you can find out. The eigenfunctions are nothing but the product function. Eigenstates are plus this energy magnetic quantum states are there here. The total magnetic quantum number of this state is 1, 0, 0, minus 1, and we have eigenvalues or the energy of each of the energy states. You consider there are these four states are identified as 1, 2, 3, and 4. For state 1, if you go into quantum mechanical analysis, we have to write down the full Hamiltonian. Total Hamiltonian is Hamiltonian of the Zeeman part and Hamiltonian for Gij part, spin-spin coupling, and work out for all the four product functions. You will get the 4 by 4 matrix. Okay, and then very easily you can work out what are the energies, and you can calculate the eigenvalues. And these are the eigenvalues of 4 energy states. But the frequencies are nothing but the difference in these eigenstates. You can find out what are these frequencies. So I have worked out here for alpha state, what you are going to get is half nu A plus half nu X plus 1/4 JAX. This is the energy or eigenvalue for this alpha state. And this is for the alpha beta state, where energy for this state is half nu A minus half nu X minus 1/4 JX. Remember, always it so happens one of the energy states will move to the from the chemical shift position. We have observed one peak move to the left, one peak move to the right by a fraction of J. It is half of J, it move to the right, half of J, one peak move to the left. How it comes? It is because when you work out these eigenvalues and look at the transitions and calculate each of the transition frequencies, you can find out these things. So similarly, beta alpha is worked out, and this is the energy state for the beta. So these are the 4 energy eigenvalues. Now remember, we know what are the possible transitions. For example, alpha, this one considers A, first one, second is X, right? First is A, second is X, AX, AX, AX. In the same order I will take. And now I have written like this. What is if the transition between 1 and 2? A has not changed its spin state. It remains as alpha. Whereas X has changed from alpha to beta. Now take the difference of these two. When I take the difference, this will get cancelled out. This half nu X plus half nu X, when I take the difference, it will become nu X, and 1/4 JX minus of minus, so it will be half JX. So one peak is chemical shift at the chemical shift at nu AX, chemical shift of X spin plus half of JX. So this is the chemical shift of X spin. One peak is moved to the right by half of JX. Now, what is other possibilities you can think of? Think of this possibility. Okay, this possibility. 3 and 4. The A spin is not changing at all its state, it remains beta. Here, X spin is changing from alpha to beta if I take the transition. So again, now to find out the difference between these two, you will find out that the frequency is such that it is nu x minus of 1 by 2 jx. So from these four energy states, what you should do is find out allowed transitions, which spin is flipping from alpha to beta or beta to alpha. This one, 1 to 2 correspond to X transition, 3 to 4 correspond to X transition. If you simple arithmetic, if you do find out the difference of these things, you will find from the chemical sheet of nu X, one peak has moved to the right by half of J, one peak has moved to the left by half of J. So it is split into a doublet. Central peak will not be there. So now without coupling, there was one peak. Now because of coupling, it's split into two, where one moved to the half of Jx, one moved to the left, which is half of Jx. So totally, the separation of this, if you measure, it is JAX. Same way, now we look at 1 and 3, where A spin is changing state, but alpha, it Bx remains alpha. Now 2 and 4, if you take again, A spin is changing state from alpha to beta, but X spin is remaining same. The state is not getting changed. Understood the logic now? So that way we can work out all the possible transitions like this. I don't have to go to this. This I described in one of the classes. Now difference in the eigenvalues, when you work out like this, I took the difference in the values between first state and second state. This is nu x plus half jx. And between 1 and 2, and difference between this is 3 and 4. Not this is 1 and 2. I'm sorry, this is 3 and 4. Then it turns out to be nu x minus half jx. You understand? I took the eigenvalues. I gave you the list, all the four possible eigenvalues for each state. First and 2, if you take the difference, you get this, and 3 and 4 here, you will get this thing. So that means these were we identified as X transitions. So from the chemical sheet of the X spin, there is a one peak at half of Jx, there is another peak at half of Jx. So minus half of Jx, so we will get doublet centered at chemical sheet of X and whose separation correspond to Jx. Same way, you can do that for 1 and 3 and 2 and 4. Now, you will get the frequency for A, and one peak is shifted from the chemical sheet of A by half Jx to the one side, and other peak is shifted from the chemical sheet of A by half Jx on other side. So that means for each of these nuclear spins, split into doublets, and you get doublets of equal intensity separated by Jx. This is what I wanted to say. This is what we observed. 1, 2, and 3, 4 transitions correspond to X with this separation. 2, 4, and 1, 3 transitions correspond to A with this is the separation. Always center of this doublet gives you chemical sheet of A here. This center of the doublet gives you chemical sheet of A. X. So now analyze of the two coupled spin system A and X, which are very well separated, weakly coupled, is very easy to interpret. Okay, it gives 4 lines of equal intensity. Get the center, you get chemical sheet of this. Get this center, get the chemical sheet of this. Simply measure one of these separations, we will get JAX. Okay, and we can also calculate the transition intensities. Okay, the transitions intensities in this case for all of them, I will say IA1, IA1, IA2, IX, IX2. These are the intensities for each of the transitions. But without working more into the details, again we can do quantum mechanical calculations. I am telling you all IA1, IA2, intensity of A1 and A2, intensity of X1 and X2 are same. So it is a ratio 1:1:1:1. The summary of AX spin system is such that when two spins are coupled, weakly coupled, you have 4 transitions, 2 for A, 2 for X, which is called AX spin system in the proper nomenclature. Separation of Any of these doublets will give you J coupling. Center of each doublet gives you chemical strength. You got the point how to analyze the AX spin system. And all of them are equal intensities. This is a very important thing you should remember. Very easy to analyze two spin spectrum. You can work out detailed quantum mechanical calculations you can make, but it's a cumbersome work. It takes a lot of time. I am giving you just an idea how to analyze. So what we will do? So we will stop today and then continue tomorrow with the analysis of one or two strongly coupled case like AB A2 spin and an example of three spins weakly coupled before we start the analysis of some other spectrum.